Our next episode or lesson in the Representing Data series is all about compression. I'm going to do an introduction about compression, about what data compression is, why we compress data, the number of different compression methods, and also how to calculate the number of bits required to store a piece of uncompressed data in ASCII. What is compression? Well, a file could be too big to store. It could be too big for us to download, or transmit, or give to somebody else. We might want to reduce the size of a file or the number of files that we need to send, or store on our hard drive. Maybe you're streaming a film and you want to reduce the amount of data that's sent. All of that uses file compression. So, when we compress the data, we're actually manipulating the structure to make the file size smaller. We're doing little simple algorithms to compress it, to make it smaller. And there are two types of compression you need to know about: lossy and lossless. Let's look at lossy first. This reduces the size of the file permanently. It's lossy. You cannot get back to it. It's permanent. The data that you're removing, though, is stuff that you don't really need. It's redundant information. It would make a very small difference to the quality. If you want to bring the file back to its original size, all that data that you did remove is gone. It was permanent. It's not coming back. Lossy compression would really be used in sound, video, image files. Reason for that is just our human frailties. The sound that we hear is only at certain ranges, and sound that's recorded can be above those ranges, so we can get rid of those. Or maybe the images that are being recorded, our eyes only notice. If you think of how a video works, it's just a series of images, a series of frames that go so many times a second. 30 times a second is normally good enough to convey movement. 60 is better. So if you've got 100 frames, you don't have to keep all of those frames, and it won't make a difference to the actual quality of the film, or not a noticeable difference anyway. And as I said, there's times you don't want to use lossy compression. You want to use lossless. You want to be able to bring it back. Let's look at an example. Here, James has an audio file he wants to send to Sabina for her to add a homework project. James wants to reduce the size of the file so it's small enough for him to attach to an email. He chooses to compress the file into MP3. Now, MP3 is a lossy compression. The changes will be permanent. What he could do is remove the background noise, any noises that wouldn't normally be heard by human ears, and that will reduce the size of the file. And when you play it back, it's just difficult to tell there's any difference between them. And then he can send that. Lossless compression. Well, unlike lossy, when you compress it, you can come back to the original file. So the stuff that you remove can be restored. Quick example, think about a zip file. When do we use lossless? Well, when it's absolutely vital that we need no data to be permanently lost. So you might need to temporarily squish it down to send it somewhere. But when it gets to the other end, we want to be able to bring it back again to its original form. To do that, you normally use an algorithm. And there's lots of those algorithms that are out there. Here's an example. Text file. So we're not talking about images or videos here. We're talking about a text file. So Marcus wants to store a quote here. Ask not what your country can do for you. Ask what you can do for your country. Wants to compress that file so it takes up as little room on his hard drive as possible, but doesn't want to lose any data. You could use some kind of lossless compression to do this. So, if he doesn't use the spaces and punctuation, it's got 61 characters in there. Each character, if you remember your ASCII character set, requires 1 byte. So that means it would need 61 bytes of storage to store that quote. But if he looks at that quote and looks at the repeating words in it, like ask, and what, and your, he could store the position where those words were used and then put them into a table and then compress it and then later on bring back those positions. So all he's done really then is store the word and the positions, and that means they only take up 49. So if you count all of these up, that's 49. So he actually has saved some space there because he just recreate all of that. When he goes to bring it back again, he goes to position 1, puts in ask, position 2 not, position 3 what, position 4 your, and so on, and recreate it. So that's a simple form of compression there. And thinking about calculations, how many bits are required to store a piece of uncompressed data in ASCII? It's quite simple really. Each character is 7 bits. Don't worry about the control bit, the 8th bit. So each character is 7 bits. So for every character, just multiply it by 7. If you have 2 characters, multiply it by 7. 4 characters, multiply it by 7. That's how many bits you have. A little bit of a research task for you to do now. Why don't you pop on the internet and go and look at each of those file formats and find out if they're lossy or lossless. And then a final thing there, how many bits would you need to follow the piece of uncompressed data in ASCII? And that's that bit at the bottom. Notice there are spaces and punctuation. Have a go, pause the video, and come back in a second once you've done that. Well, here's your answers. So the lossy ones are the red ones, the MP3s, OGG, MP4, WMV, GIFs, and H.264s. And then the green lossless ones are the WAVs, RAWs, bitmaps, and PNGs. Question number 2, there were 39 characters there, including the spaces. So that's 39 times 7 is 273 bits. Simple, eh? Well, show me. Go on to Edmodo, have a go at the representing data compression quiz. Once you've done that, come back here. What do we do today? You should now understand what data compression is. You should understand why we compress this. You should know about the 2 different methods, lossy and lossless. And you should also be able to calculate the number of bits that we would need to store uncompressed data in ASCII, multiplied by 7. Thanks. I'm going to move on to run length encoding in the next episode. Cheers.